Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today we're going to begin our discussion of functions of the form f mapping some domain contained in Rn, but outputting values in a set of real numbers. An example might be z equals x squared plus y squared. You can see how we're outputting z with the corresponding input of the point x, y. That's like saying, if you have some domain down here in the xy plane, for each of those points in the xy plane, you'll output some height. What you'll end up with is a surface. It should make sense that you should get a surface from such a creature, since after all, you have 2 degrees of freedom here, 2 degrees of wiggle room. You can freely adjust x and y, but the value of z will be determined by that. You should end up with a 2-dimensional object embedded in a 3-dimensional space. If I have w equals some function of x, y, and z, then I have 3 free choices and 1 constrained choice. 3 independent variables and 1 dependent variable. We call this a hypersurface. In fact, any expression of this form ends up being 1 dimension less than the 4-dimensional variables that you have. A hypersurface, more generally, is a surface of codimension 1. That means 1 dimension less than the space that you are embedded in. So more generally, if I have z is some function of x1, x2 through xn, then I have an n plus 1 dimensional space in x variables and 1 z variable, but I end up with an n-dimensional surface or object embedded in R n plus 1. That is an object of codimension 1, and therefore this too would be a hypersurface. The domain of a function is, of course, everything that you plug in that produces an output. Let me give you an example. Suppose I have z equals the square root of 9 minus the quantity x squared plus y squared. This is our function. It has 2 independent variables, x and y. What is its domain? Let's suppose that we are interested in only those values that produce a real number output, nature of this particular course. The question to ask yourself is, what can go wrong? When you're taking square roots, the thing that can go wrong is you might get a negative under the radical. We have to guarantee that the thing under the radical is non-negative, and rearranging this will have x squared plus y squared is less than or equal to 9. That represents all the points within a circle of radius 3, including the boundary, centered at the origin. Altering this last example by just a little bit, suppose I have a function which is 1 over the square root of 9 minus the quantity x squared plus y squared. When you ask the question, what can go wrong? Now there are 2 things that can go wrong. Not only can you get a negative under the radical, but you can get division by 0. Division has that nasty little problem. You can't divide by 0. So in this case, we have to be sure that 9 minus the quantity x squared plus y squared is strictly greater than 0, and hence x squared plus y squared is strictly less than 9. Now, what you end up with is the interior of the circle of radius 3, but not the boundary. If I write w is some function g of x, y, and z equal to 1 over the square root of 9 minus x squared minus y squared minus z squared. Now, the domain requires that x squared plus y squared plus z squared is strictly less than 9. The domain is in R3. And we have to think of it like this. It's all the points within a ball of radius 3, but it's kind of like a peeled grape. Everything but the skin. All the interior, but not the boundary surface. If you have a surface of the form z is a function of x and y, for each x and y in the domain, you produce a height generating some kind of surface. If you set z equal to a constant, that takes that constant c and cuts off the surface and selects the points at that level. This is called a level curve. You should get a one-dimensional object embedded in a three-dimensional space. You're setting z equal to a constant, and what's left over has only 1 degree of freedom. If you choose x, y will be determined by the equation. If you choose y, x will be determined by the equation. You will have only 1 degree of freedom, so you end up with a one-dimensional object embedded in a three-dimensional space. Cut off at a level height, it is a level curve. As an example, consider the curve, the surface. The surface, z equals x squared plus y squared. Can you identify that quadric surface? Yep. That's an elliptic paraboloid opening up. You can see z values can't be negative because they're equal to something that is positive. Now, if you set z equal to a constant, the level curve is a circle. We can plot level curves in the xy plane, which represents part of the domain. If you set z equal to 4, you get a circle of radius 2. So we had z equals 1. The circle of radius 2 corresponds to z equals 4. And a circle of radius 3 corresponds to z equals 9. You get a kind of topographical map with the elevation lines showing at different values of z. In direct analogy, if you have w equals a function of x, y, and z, and you set w equal to a constant, how many dimensions is there in an object like this? It seems to me you have 2 degrees of freedom, and the third variable is determined by this equation. You end up with a 2-dimensional object. This is going to be called a level surface. So for example, if I have w equals x squared plus y squared plus z squared, for each w equal to some constant, I end up with a sphere of radius square root of c, provided c is not negative. Now, this is a calculus course. Calculus is part of analysis. Analysis is, in mathematics, limits and their applications. The regular progression when we introduce a new class of functions is to first talk about limits, and then talk about derivatives, and then integrals. Before getting too deep into our theory of limits, we have to talk about the topology of Rn, and in particular the usual topology of Rn. This may be a new word for you. Sometimes students misconstrue this word as being like topography, which is not what this is about at all. A topology is everything you want to call an open set. I can give you a definition. Let X be a set. A topology T on X is a collection of subsets of X such that the following three properties are satisfied. First, both the empty set and the set itself must be elements of the topology. They must be defined as open sets. By the way, we'll define a set to be open with respect to a particular topology if it is an element of that topology. So everything in T, the topology, is what you call an open set. Also, if U lambda is in the topology for all lambda elements of some indexing set capital lambda, then the union for all of these lambdas in the indexing set of the U lambdas will also be an element of the topology. In other words, every topology is closed under arbitrary unions. If you take the union of two open sets, you will get an open set. If you take the union of a million open sets, it's still open. If you take a union of an infinite number of open sets, that too must still be open. Finally, if U sub k is an element of the topology for k lying in some initial segment of the set of natural numbers, then the intersection, as k goes from 1 to n of U sub k, will also be an element of the topology. In other words, topologies are closed under finite intersections. Not infinite intersections, but only finite intersections. If you take two open sets and find the intersection, what you get will be an open set. If you take any 1 million open sets and find the intersection, that too must be open. But it is possible to take an infinite number of open sets, take their union, and end up with something that's not open. Let me give you an example. Suppose we look at the intervals, let's say I sub k equals the open interval, let's say negative 1 over k, 1 plus 1 over k. Now, these are open intervals that are contained in the set of real numbers. On the number line, if this is 0 and this is 1, this backs off from 0 just a little bit, and this one backs off from 1 just a little bit in the other direction. And you end up with something that contains everything between 0 and 1, plus a little bit of overlap on each side, but does not contain these endpoints. If we take the intersection of these, as k goes from 1 to infinity, then 0 and 1 is indeed an element of every single one of these I sub k's. But they get closer and closer, wedging in on there. Any point bigger than 1 will not be in the intersection. Any point less than 0 will not be in the intersection, because you'll be close enough eventually to exclude that point from the intersection. So the intersection is the closed interval from 0 to 1, because 0 and 1 is in every single one of those intervals. It must be in the intersection. So here you can see that you can take an intersection of an infinite number of open intervals and end up with something that is not open. It contains both of the endpoints. Now, there are many different topologies that one may impose on a particular set, and the topology that you choose will determine which sequences converge and which diverge, which limits exist and which limits don't exist. So, what is the usual topology on Rn? We'll begin with defining what we mean by an open ball. We're trying to get at the idea of one of those little peeled grape thingies we looked at earlier. The set of all points in a ball of some radius r, centered at some point x naught. The open ball centered at x naught of radius r is denoted by the ball of radius r centered at x naught and defined by this open ball of radius r centered at x naught is the set of all points x in Rn such that the distance between x and x naught is less than the radius r. Notice, by making a strict inequality, we are excluding the points on the surface, giving only the peeled grape, the interior part, but not the boundary surface. This is the open ball, centered at x naught of radius r. The closed ball is defined in a similar way. First of all, it will be denoted by B with a bar, indicating we're kind of putting the peel back on the grape. And defined by closed ball, it's the set of all points in Rn such that the distance between x and x naught is less than or equal to r. So with the conditional inequality, we get the surface put back on. We're going to make a clear delineation between the word sphere and the word ball at this point. From now on in this course, a sphere is a surface and a ball is a region bounded by a sphere. So a ball contains the inside of a sphere, whereas the sphere is just the surface itself. So from now on, you'll know basketball is not really a ball, it's a sphere, whereas a baseball is a ball. In R3, an open ball looks like a solid ball. But what is an open ball in R2? In R2, it's really an open disk. And what about in R1? A set of points no more than a certain distance away from some center x naught. In R1, an open ball is an open interval. Now that we've defined what we mean by open ball, let's define what we mean by open set. A set S contained in Rn is called open if each x lying in S, there exists some r, a radius r greater than 0, such that the ball of radius r centered at x is a subset of S. Let me give you an example. Suppose we have some generic kidney-shaped lamina without the boundary curve. At each point within this set, you can find an open ball small enough that that open ball is entirely contained within the set. And that's true no matter how close you get to the boundary. You can always just choose the radius to be so small that that little ball will lie entirely within the set. If, on the other hand, I take a generic kidney-shaped lamina that includes the boundary curve, no matter what point I choose on that boundary, and no matter how small I make that radius, that ball will have points that are outside of the set S. So this set that includes the boundary curve is not open. This that does not include the boundary curve is open. There's something that you should note that is true of all open sets. Since every point inside of an open set has an open ball that you can stick around it, and that open ball stays within the set, these little open sets can be stuffed full of these peeled grapes. Around each and every single one of those points, you can fit a peeled grape, one of these little open balls. That's not necessarily true for sets that are not open. If I just have a curve segment, that set is not open. No matter what point you choose on that curve, and no matter how small that radius is, there are going to be points on a ball centered at that point that do not lie on the curve and hence are not in the set. So sets that are not open don't have to be very fat. They can be quite thin, but open sets are fat. You can stuff them full of grapes. This brings up some new terminology. Let's consider our generic kidney-shaped lamina. Points on the interior have little open balls around them that fit within the set. Points on the boundary are such that every open ball will have points both inside and outside when centered at a boundary point. This leads to two definitions. We say that X is an interior point of a set S if there exists a positive radius such that the ball of radius r centered at x is contained within the set S. So on interior points, you can always fit a little open grape around that point, and that little open grape will lie entirely within the set S. X is a boundary point if for all positive radii, the ball of radius r centered at x contains points in S and points not in S. So your boundary points will be such that every open ball, no matter how small the radius, will have points both inside and outside the set S. Note, every point in an open set is an interior point. that set. Open sets consist only of interior points. Also, in R1, the ball of radius r centered at some x naught is going to be the interval from x naught, vectors in R1 are scalars, minus r to x naught plus r. Everything from here at x naught minus r to here at x naught plus r, x naught being right in the middle. Also, every open interval is open if you're going from A to B, not inclusive of the endpoints. Then any point in there can have a small enough little open interval around it, a small enough little open ball, that it will lie entirely within the open interval. So every open interval is an open set. The set of boundary points of a set S is denoted by, and it's a fancy D and then S. I will often write it like this, though the old style way of writing it is like this. So this contains only boundary points. This old style D is used for several purposes in this course, as you will see. Not only is it used to denote the boundary of a set, it will be used to denote partial derivatives later on. People used to write, back before the Civil War, the letter D, especially a letter D terminating at the end of a word, with this fancy little scrawl over it. They might write in a will, the land. Sometimes that D goes way over the entire word. I wanted to show you an example of an ancient document that uses this curly Q D on it. Let me grab this. This is a part of a will that belonged to an ancestor of mine. And you can see these funny little D's. Here's the word God with the curly Q D. This will was inscribed in 1824. You can see that he was being weak in body and talking about the body. Here's a D that is not a terminal D. Here's a judgment, J-U-D-G-M-E-N-T. Judgment, the D is the curly Q D. Often, even if it's in the middle of a word, they use that. Here's the word 124. So I thought you would get a kick out of seeing this old style D in an old document just as it was written in 1824. I would like to look a little more closely at this idea of the boundary of a set. Suppose my set S in R1 is the interval from 0 to 1, including the endpoints. We're including the endpoints here, so it's customary to fill in these little circles. You can see that the boundary of S is the set that contains 0 and 1. Only 0 and 1 are boundary points. No matter what little open interval you put around 0, you will have points inside the set, but also points outside of the set. And the same is true at 1. No matter what little open interval you put around that, that open interval will have points both inside and outside of the set S. So the boundary of S is the set that contains only these 2 points, 0 and 1. Now,
What if my set S is the open interval from 0 to 1? Here we have 0 and 1, and the points in between, but not the endpoints. What is the boundary of this set? Well, it turns out it's the same thing. Yes, 0 is still a boundary point because it is still true that no matter what little interval you put around that, you'll have points outside of the set and also points inside of the set. Same thing true at 1. Points outside and points inside, no matter how small you make that little open interval. So even if a point is not in a set, it can still be a boundary point. It lies at the edge, and that's okay. In the last example, you can see our closed interval contained all of its boundary points. The open interval contained none of its boundary points. So if S is the closed interval from 0 to 1, the boundary of S is the set that contains 0 and 1, and the boundary of S is a subset of the set S. On the other hand, if S is the open interval from 0 to 1, the boundary is still the set that contains 0 and 1, but now the boundary intersected with S is empty. There are no points in the boundary that are also in the set S. We're now able to define what we mean by a closed set. A set S is called closed if it contains all of its boundary points. Id est, that is, the boundary of S is contained within S. That's what it means to be closed. A set is open if it contains only interior points. A set is closed if it contains all of its boundary points. The complement of a set S is denoted by S with a superscript of C and defined by SC is the set of all X such that X is not in S. So the picture is like this. Let's suppose this is our universe, and here's your set S. S complement is everything else. As an example, suppose S is the open interval from 0 to 1. S complement is everything from minus infinity to 0, including 0, union everything from 1 to infinity. Note that S is open. Is S complement open, closed, or neither? Those are the three options. Remember what the definition of a closed set is. A set is closed if it contains all of its boundary points. But there's a special thing you have to keep in mind. Infinity and minus infinity aren't points. The only boundary points of S complement are 0 and 1, and they are both included in S complement. Therefore, S complement is closed. The boundary of S complement is the set that contains 0 and 1, and those are indeed inside of S complement. We can't think of infinity or minus infinity as points because they're not even defined. For example, suppose S is the interval from 1 to infinity. This set is closed. S complement is everything else from minus infinity to 1. So S is here. S complement is everything else from minus infinity up to 1. And this is open. Every point is an interior point. If my interval includes 0 but excludes 1, sometimes we say this is half open, half closed. But in truth, this set is neither open nor closed. It's not closed because it does not contain its boundary point at 1. The boundary of this set is the set that contains both 0 and 1. And that's not a subset of I, so I is not closed. But it's not open either, because it contains 0, and 0 is not an interior point. It is a boundary point. So this set is neither open nor closed. Can you think of a set that is both open and closed? Suppose your set S is the entire real line. Its complement is empty. Its boundary is empty. It has no points on the boundary. So surely the boundary is contained in S because the empty set is a subset of every set, and hence a subset of the entire real line. Since the boundary is a subset of the set S, R is closed. It contains all of its boundary points, and that's kind of a vacuous statement because it has no boundary points. But even so, the empty set is a subset of R. That's a true statement. So R is closed. But R is also open because around each point in R, you can put a real little open interval, and that interval will be contained in the set of real numbers. So R is open. Every point in the real line is an interior point. So R is both open and closed. What about the empty set? The empty set contains all of its boundary points because it has no points. Any point in the empty set might be thought of as a boundary point because there are no points in there. Also, if you have a point in the empty set, you can always fit an open ball around it, and that's a vacuously true statement because there are no points in the empty set. So the empty set is also both open and closed. So there are two sets, the entire real line and the empty set, and those sets are both open and closed. You may have seen the following theorem coming along. S is open if and only if S complement is closed. Proof. This is an if and only if statement. We have to prove this in both directions. Both S open implies S complement is closed, and S complement is closed implies S is open. If S is open, then the boundary of S intersect S is empty, and that implies the boundary of S is contained in S complement. But remember what the boundary of S is. Boundary of S is the set of all X such that the open ball of radius R centered at X will contain points both in S and points not in S. You can see that if you have some set S, If this is S and this is S complement, a boundary point for S will also be a boundary point for S complement. I have points in each. But since the boundary of S is contained with S complement, we deduce that the boundary of S complement is contained in S complement, and that implies S complement is closed. It contains all of its boundary points. Now we need to prove the implication in the other direction. We still need to prove the implication in the other direction, which was if S complement is closed, then S is open. The positive is if S is not open, then S complement is not closed. If you prove the contrapositive of a statement, that's equivalent to proving the statement itself. So we're going to suppose S is not open. That means it has a point that is an interior point. What does that mean? Remember, interior points are such that you can find a radius small enough so that an open ball around that point of that radius will be entirely contained within that set. Then, for all positive radii, the ball of radius r sin x naught contains points not in S, but it also contains the point x naught, and x naught is in S. What does that mean about the point x naught? Every open around it contains points in S and points not in S. It's a boundary point. So the set S has a boundary point in it. That means if you take the boundary of S and intersect with S, you don't get the empty set. That also implies that since the boundary of S complement is the boundary of S, then the boundary of S complement has points not in S complement. It's not a subset of S complement because it has a point inside of S. Therefore, S complement is not closed because it does not contain all of its boundary points. We say that N is a neighborhood of x naught if, first of all, x naught is an element of the neighborhood and N is open. So a neighborhood is just an open set that contains the point in question. Any open set that contains that point will be a neighborhood. A punctured neighborhood, or a deleted neighborhood, of x naught an open set n such that the idea being, if this is your point x naught, we're going to take this set n to be such that it doesn't contain the point x naught. We're taking an ice pick and poking that out. But if you were to throw that point back in, you would end up with a neighborhood. So first of all, we want x naught to be not an element of n. But if you take n and union to that the point x naught, you get a neighborhood. Of x naught. So you can see for punctured neighborhoods, they have to be open, but you have to remove the point in question. That ends up being a punctured neighborhood of the point x naught. Now, let's suppose that f maps some domain contained in Rn and outputs in R. What do we mean by the limit as x goes to x naught of f of x equals some limiting value L? What do we mean by this? Let's go back and review the notion of limit as we've seen it so far. In Cal1, when we talked about the limit as x goes to a of f of x equals L, that meant for all epsilon greater than 0, there exists delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, that implies the distance between f of x and L is smaller than epsilon. I thought you'd like to see this definition of limit expressed without words. Notice that in the domain, we're avoiding the point A itself and only looking at points within some punctured neighborhood. If this is A, we're taking that out and then looking on an open interval around that, but excluding the point A itself. This is a punctured neighborhood. In the range, we're looking at points close to L that are some epsilon away. This is a neighborhood of L. We could make our definition even more general. The definition that we've given here requires that we be able to take absolute values of differences. If you can't subtract points, you still might be able to come up with a notion of limit if you can come up with a notion of topology. Yes, topology is all that's needed, a notion of neighborhoods, open sets, and punctured neighborhoods. I guess we could have defined the limit as x goes to a of f of x equals L as follows. For any neighborhood in of L, there exists a punctured neighborhood in hat of A such that if x is in hat, if it's to within that punctured neighborhood in the domain, then f of x lies within a neighborhood of L. This could have been our topological definition. As you can see, we can define limits on spaces that don't even have a normal metric, a way of measuring distance. By the way, topology is a whole branch of mathematics. You can specialize in topology. There are two main branches. There's point set topology and there's algebraic topology. These are massive areas in mathematics. They get broken down into specializations and subspecializations. What about vector valued functions? functions. Remember, we had the limit as t goes to t naught of r of t equals some value L. That meant for all epsilon greater than 0, there exists delta greater than 0, such that if 0 is less than the distance between t minus t naught is less than delta, that implies that the distance between r of t and L is smaller than epsilon. Again, you can see a punctured neighborhood. We'll often denote that by NBHD in mathematics. And in the range, we have a neighborhood of the limit value L. Once again, you can see that we could have generalized this definition of limit using topological notions. Are we speaking Martian yet? I now want to look at what happens in the limit as x goes to x naught of f of x equals L. What do we mean in the present case? These are the sorts of functions that we are dealing with now. And it will begin with, of course, for all epsilon greater than 0, there exists delta greater than 0, such that the domain now consists of vectors. So you want to be within some ball in the domain no bigger than radius delta. This is the ball of radius delta centered at x naught. But we're excluding the point x naught because of this. This implies that the distance between f of x and L will be smaller than epsilon. Once again, you can see that we're dealing with, in the domain, a punctured neighborhood of x naught. And we're getting to within some neighborhood of the limiting value L, no further than epsilon away. You can see we're requiring closeness in the domain to the point x naught, implying closeness to L for the functions in the range. Now there is a little bit of a caveat here. We're requiring closeness within the domain to imply closeness in the range. It's possible that you can approach the point x naught along straight paths and all arrive at the same limiting value L on those straight paths. But if you approach on curved paths, you can get different limits. So just because you're getting one particular limiting value on a certain class of paths doesn't mean you've checked all possible paths. Different sorts of paths might give you different limits, and there are significant examples where that's the case. You would have to check all possible paths, including paths that do all kinds of crazy things, in order to verify that the limit value is L. And it's just not possible to check the limit on all possible paths. But if you have two paths, path 1 and path 2, that give you different limiting values, L1 and L2, that is sufficient to say that the limit as x goes to x naught of f of x does not exist. Different limits on different paths implies the limit does not exist. Back in R1, there were only two ways you could get to A, from the left and from the right. You'd had to get the limit from both sides to be the same in order for the limit to exist. So if you approach from the left and the right and get the same value, then the limit exists and it's equal to the common value. But that's not going to be the case here in R2 or higher because there are so many different ways you can approach. You can go straight in, you can go curling in, any number of ways. You can zigzag in. There's so many different potential paths. There aren't just two directions anymore. And it's not just approaching from every linear direction. That's not enough either. Curved directions might give you different values than straight paths. I want to explore our definition of limits by looking at the limit as xy tends to 0, 0 of x squared y divided by x squared plus y squared. You can see that if you plug 0, 0 in, you end up with 0 divided by 0. And in the context of limits, 0 divided by 0 means more work. So what do you suspect happens as x and y get closer and closer to the origin in the plane? Let's explore this by graphing this surface and seeing what happens.
I'm going to define my function as something that takes x comma y and outputs x squared times y divided by x squared plus y squared. And I'm going to plot 3D my function where x values go from, say, -1 to 1, y values from -1 to 1. Oops. I'm going to constrain the view to go from -1 to 1, -1 to 1, and -1 to 1 on the z as well. I'm going to constrain the scaling so it has the same size units on each of the axes. And here's our surface. Let's put some regular old axes on there. As you get closer and closer to the origin in the xy plane, the z values seem to all be going to 0. So it looks like you might hypothesize, just based upon the graph of this surface, no matter what direction you're going, as you go in towards the origin in the xy plane, the z values get closer and closer to 0. Aha! You can see that that's true because in our function, you have a cubic polynomial in the numerator and only quadratic terms in the denominator. If you take tiny numbers and cube them, let's say 1/1000th cubed is what, a billionth? Whereas if I'm dividing by 1/1000th squared, it's still just a millionth. A billionth over a millionth is still going to be about 1/1000th. So the top is getting smaller faster than the denominator. And that can be seen right there on the graph. That's why all points go through the origin as x and y go to 0, 0. If we change this function a little bit and had a quadratic numerator and quadratic denominator, that changes the graph quite a bit too. You can see that as you go towards the origin, let me put the axes back in. There's your origin down here. There's a little gap. The gap is a defect of the plotting mechanism. You need to plot more points to close that gap. But you can see that as you go along one axis, the z values are going to be 0, but as you go along another axis,
the z-values are all 1. So you get different limits approaching the origin in different directions here. This little crumpled graph. Let's go back up and take a look. If, say, x is equal to 0, that means you're on the y-axis in the xy plane, and y is not 0, these ratios will all be 0. So if you're approaching on the y-axis, you get 0. But if, on the other hand, y is 0, but x is not 0, then the ratios are all 1. So if you're on the x-axis, you'll have 1 as the limit. And you could see that right there in the graph. The x-axis gives you 1, the y-axis gives you 0 for the limit. Aha. Let's go back to the problem that we are originally addressing here. We expect to get 0. Is there some way to use the definition of limit to prove that the limit is 0?
As we saw in the graph, we expect to get a value of 0 for this limit, the top being cubic, the bottom being quadratic. But how do we prove this? Let epsilon greater than 0 be given. As all good limit proofs begin, we want the difference between the function and the limit to be less than epsilon. Notice that this is the same thing as x squared over x squared plus y squared times the absolute value of y. Let's start playing with this expression here. Note that x squared over x squared plus y squared times the absolute value of y, which is equal to this thing which we want to be smaller than epsilon, is less than or equal to x squared plus y squared over x squared plus y squared times the absolute value of y. If you increase the numerator by some positive amount, you're going to increase the size of this fraction, but that's 1. Now, the absolute value of y, as you know, is the square root of y squared, which is less than or equal to the square root of x squared plus y squared. Well, that's the norm of the vector xy. And remember, we're taking the limit as xy tends to 0, 0, 0. You can see right away that the norm of the vector xy is the norm of the difference between xy and the place that we're going to. We need this to be smaller than delta, but we also need it to be smaller than epsilon. So why don't we set delta equal to epsilon? Then, whenever 0 is less than the norm of x minus 0 is less than delta equals epsilon, we have the function value is no more than epsilon away, since this will be equal, no more than epsilon away from the limiting value. We will automatically have the difference between x squared y over x squared plus y squared and 0 will be smaller than that epsilon. And that proves that the limit as x goes to 0 of x squared y over the quantity x squared plus y squared is in fact 0. If we look at the other example that we graphed, x squared over the quantity x squared plus y squared, and wonder about the limit as x goes to the 0 vector of x squared over x squared plus y squared, we can prove that this doesn't exist by looking at two paths. On path 1, we'll look at r of t equals t0. This is the x-axis. And we'll look at what happens in the limit as t goes to 0 when we evaluate this function on this curve. This will get us to 0, 0. But it's only along the x-axis. You'll end up with t squared over t squared plus 0. That has a limit of 1, just as I said before. What about on path 2? The y-axis. We'll take the limit as t goes to 0 of our function evaluated at 0t. In this case, that's the limit as t goes to 0 of 0 divided 0 squared plus t squared. Well, the numerator is always 0, so you get 0 for the limit here. Because you have different limits on path 1 versus path 2, we deduce that the limit does not exist. The limit as x goes to the 0 vector of x squared over x squared plus y squared does not exist. As you know, each time we introduce this new epsilon delta notion of limits, we try to get away from it as quickly as possible. We need some theorems. First of all, in the limit as xy goes to ab of x, you should get a. As the point xy tends to the point ab, the x-coordinate, of course, should tend to a. Also, if the limit as x goes to x naught of f of x is L, and the limit as x goes to x naught of g of x is M, then in the limit as x goes to x naught of f of x plus g of x will be L plus M, of course. And if you put a minus here, you'll get a minus there. What about products and quotients? Of course, in the limit as x goes to x naught, f of x times g of x, you'll get L times M. And we know that division has its nasty little problem. You'll get L divided by M provided M isn't 0. Also, it follows as an immediate corollary to the last theorem that if P is a polynomial, then in the limit as x goes to x naught of P of x, you get P of x naught. So you can evaluate limits of polynomials by simple substitution. Similarly, if you're dealing with a rational function, you can substitute as long as you don't get 0 in the denominator. So for example, if we're taking the limit as xy tends to 1, 2 of x squared y over x squared plus y squared, these limit laws allow us to break quotients into the limit of the top over the limit of the bottom. The limit of the product is the product of the limits, etc., etc. You just end up with substitution. So you're going to get 2/5. I want to look at another little example. The limit as x goes to the 0 vector of x squared minus y squared over x squared plus y squared, quantity squared. Let's try some paths. Path 1. R of t equals t0, the x-axis. If we take the limit as t goes to 0, you'll end up at the origin. And when you plug in y equals 0, x equals t, you'll get t squared minus 0 over t squared plus 0 squared. The limit is clearly 1. Let's try path 2. The y-axis this time. Take the limit as t goes to 0. X is 0 this time, so you get minus t squared over positive t squared, and the limit is still positive 1. But that's not the end of the story. We get the same limit if we approach on each of the coordinate axes. Let's try the following path. Path 3. This is the 45-degree line in the xy plane. We'll take the limit as t goes to 0. T squared minus t squared is 0. As long as t is not 0, you're going to get 0 divided by not 0. That's 0. The limit is 0 if you go along the 45-degree line towards the origin. We deduce then that this limit does not exist, though you might want to see the graph.
I'm going to come up here and change our function a little bit. I take this and square it. There's our function. Now let's see what this thing looks like. You can see, let's see where the axes are. The axes gave us limits of 1. As you go along the axis toward the origin, you end up with 1. But if you go along a 45-degree line, y equals x or y equals negative x, you end up with the limit value of 0. It looks a little choppy in here, and that's a defect of the programming on this graphing device. This is Maple. We can add more points to make the graph a little better. It's still going to have a problem towards the origin, but you can see a little better now that along the coordinate axes, the height is 1 heading in towards the origin. Along the 45-degree lines, you get 0. Looking from below, get 0 on the 45-degree lines. Explaining why, in this case, the limit does not exist as you approach the origin. It depends, what you get depends upon how you approach the origin, on what paths. I would like to look at a slightly different function as well. I'm going to take the numerator and replace it by 1. And the denominator is just going to be the quantity x squared plus y squared. What do you get now? Well, it might be a little hard to see from this particular vantage point. We're going to have to back out and view this from a slightly bigger perspective. Let's see, I'm going to go from minus 10 to 10 on each of the coordinate axes now. Minus 1 to 1 just isn't going to hack it. We're getting a good view of what this thing looks like. As you can see now, as you get closer and closer to the origin, this thing blows up. Let me put those axes in there. The z coordinates will blow way up as x and y gets closer and closer to the origin. That should make some kind of sense because, after all, if you're plugging in tiny numbers into the denominator, tiny numbers, 1 over tiny, you'll recall, is huge. And 1 over huge is tiny. So, of course, if the point xy gets close to the origin, then both x and y become tiny, in which case 1 over tiny squared for that matter, is huge. If I have an x coordinate equal to, say, 1/1000th, and I square it, I'll have 1/1,000,000th. When I take 1 and divide by 1/1,000,000th, I get 1,000,000. So if y is 0 and x is 1/1000th, this function will have a value of 1,000,000. It'll get really, really big the closer you squeeze in towards the origin.
As you can see, we want some way to say that in the limit as goes to x naught, f of x equals, say, plus infinity. In particular, we just saw in the limit as x goes to 0 of 1 over x squared plus y squared. We want that to say plus infinity. You do this the same way you did in Calculus 1. The limit as x tends to x naught of f of x equals infinity means given n greater than 0, a measure of bigness in the range, there exists a delta greater than 0 such that if 0 is less than the norm of x minus x naught is less than delta, so x doesn't stray more than delta units away from x naught in the domain, then the function value will be bigger than the measure of bigness it shows. That's what the definition for limits being equal to infinity will mean. What do we mean by a function being continuous at some point? A function f is continuous at x naught if, 1, the limit as x tends to x naught of f of x exists, 2, f of x naught is defined, and 3, of course, in the limit as x goes to x naught of f of x, you get f of x naught. So a function is continuous if the limit exists at that point, the function value is defined, and the limit value equals the function value. Same old, same old. You've been doing that since Cal. These are the 3 conditions for continuity. I should also point out that we had this condition for all polynomials and for rational functions as long as we weren't getting 0 in the denominator. We deduce then that polynomials are continuous in the entire domain of Rn, whereas rational functions, do you remember what a rational function is? Is it a function that talks and makes sense? No, a rational function is a ratio of 2 polynomials. As long as you're not dividing by 0, you'll be at a point of continuity. We also have the usual theorems. F and G continuous. A constant times f is continuous. Just multiplying a function by a constant doesn't rip the function apart, doesn't cause a failure of continuity. If you add 2 functions, you get a continuous function. If you multiply continuous functions, you get a continuous function. If you divide continuous functions, you get a continuous function provided you're not dividing by 0. Discuss the continuity of f of x comma y equals, let's say, x plus y over x minus y. Both the numerator and the denominator are polynomials. Both terms in the numerator are of degree 1. Both terms in the denominator are of degree 1. You only have problems with continuity if you get division by 0. So only places where x minus y equals 0 are points where we fail to be continuous. Those are places along y equals x. In other words, f is continuous on all of R2 except the points x, x. Those are the points where y and x are the same. Let's do the same thing for the function, say, x over y minus x squared. Again, we require y minus x squared not to be equal to 0. If it is 0, y equals x squared. So this function will be continuous everywhere except on the parabola. So it's continuous in here and continuous out here, but it's not continuous on the parabola. So this is continuous on R2 except for the points where y equals x squared. Continuing on this theme, suppose I have the function f of x, y, z equal to 1 over x squared plus y squared minus z. Where is that continuous? Well, everywhere in R3 except where x squared plus y squared minus z equals 0. What kind of surface is that? Isn't that a quadric surface? Didn't we study these? Name it. Don't just point and grunt. We are not troglodytes. Go, ugh, ugh. No, it has a name. It's an elliptic paraboloid. So we're continuous everywhere except for points on that elliptic paraboloid. Those are points x, y, x squared plus y squared, such that x and y are real.